Hey guys, Mr. Ritz here. So I'm going to help you out with the beginning of the 1.4 notes in calculus. So with 1.4, we're going to be looking at this thing known as continuity. And then we're also going to look at one-sided limits that help explain some of the continuity as well. So today we're going to try to make sure we hit kind of this first goal here, is to determine continuity at a point and continuity on an open interval. So throughout the whole course of the thing. So continuity at a point exists if or we can pretty much say a function is continuous at C, whether the three conditions are met. First, that means f of C is defined. All right, so if you don't know what that means, let me get my clicker here, is that there is a point on the graph. So that means like if I have a function here, at the point C, there is a dot. F of C is defined. The other thing is that there is a limit of f of C, meaning the graph is going towards, from the left and from the right side, the same value. And then that the limit of as x approaches C of f of x is equal to f of C, meaning like we can't have a scenario where we have an f of C that exists, but the limit is going towards a different spot. So we would say that this is continuous at C if there's a point and the limit is going towards that point. And we can pretty much say if as long as this works for every point that this is continuous on the entire open interval. Now typically we would say anywhere from negative infinity to infinity. Sometimes we have to be specific, like we're talking about like a square root function is continuous, but only from 0 to infinity. It isn't with negative infinity or any negative numbers. Okay, so that's what continuous means. So we can use this, oh, kind of click the wrong button there, to help describe some other things. Pretty much what works with continuity is discontinuity. So where things are discontinuous, and we can describe those as two different types. We could have removable discontinuity where we'd have a point here where the graph doesn't have a value at the location, but the limit goes towards that value. So like we could still say like the limit as x approaches C exists. But we would say this is non-removable when the limit is going towards two different spots. So the limit as x approaches C does not exist. That would be non-removable. So you can almost see like if there's a separation or a gap or almost like a vertical asymptote, we'd say that's non-removable. And so like this example here, even though we have a location for C, we have a spot for it, the limit doesn't match. But since it's going towards a location, we would say that's removable discontinuity. Now the reason why it's called removable will make sense in a little bit here, but let's just look at a graph and see like if there's a hole in the graph, it's removable. If there's a jump in the graph, it's non-removable. Okay, so let's try to look at these functions here and let's look at them at a graph and then let's also look at the functions itself. Sorry, lost the train of thought. So I'm going to open up Desmos here. All right, so let's look at 1 over x. Let's start graphing here. I got too many noggins up here. All right, 1 divided by x. So if we look at here, there's a big jump here at 0. So we would describe this as discontinuous. I'm going to just abbreviate at x equals 0. And if we wanted to describe that discontinuity, we could say that's non-removable. All right, I'll be late, and maybe even I'll just say NR for non-removable. All right, now if we look at this, we could kind of figure that out without graphing it, because remember, we can find discontinuity points whenever a denominator would equal 0. So our denominator is just straight up x. When would x equal 0? Oh, that's when x equals 0. All right, so that's how we can find the discontinuity point. So if we look at this problem here, we can know that this is discontinuous at x equals +1, because if I plug +1 in for here, it'd make our denominator 0. Now the question is whether this is removable or non-removable. So let's graph this. This is where it gets difficult here. I have to, no, I can leave that up. I can do this, click here. Oh, all right, cool. So we got x squared minus 1. Need to divide that all by x minus 1. So I don't see a big jump in the graph. I'm just going to go over to 1 here to see. Yep, there is a hole there. So this is removable discontinuity. Or we could probably just say R here if we're getting lazy. Okay, so let's look at the equation, see if we can try to figure out why this is called removable. Remember, if we wanted to evaluate the limit when we go towards a number, we could factor the top, and the top would factor to an x plus 1 times x minus 1, and then the whole equation would be over x minus 1. Well, what happens here when we rewrite our expression, we remove the x minus 1, which removes this discontinuity point. In the first problem here, we could never remove the x. We couldn't factor it out. We couldn't multiply by conjugate. It could never get removed. So this discontinuity is non-removable because we can't factor it out and get rid of it. But this discontinuity, we can. So that's why it's called removable discontinuity. All right, let's look at a couple other examples. Let's look at piecewise functions here. No, I don't want to clear. Let me see if I can just erase this a little bit. There, that's better. All right, so a piecewise function. Let's see if I remember how to graph this. If I do x plus 1 or any x less than 0. No, that's not. Okay, give me a minute. I'm going to pause my video. I'm going to look how to type this up on. All right, so what we have to do on Desmos here is to check. We got to kind of put this in this like little bracket thing here, and we got to say like for any x less than a 0, technically it should be less than or equal to. I just don't feel like looking up that symbol here. I just know that it's going to be a solid dot at the end here. And then if I want to do this one, I'd have to do bracket, no, squiggle bracket x greater than 0 colon x squared plus 1. Okay, so if we look at these two graphs, there could be potential discontinuity at 0, because this would be if I know x plus 1 that doesn't have a denominator, that's not going to be discontinuous at all. X squared minus 1 also doesn't have a denominator, that's not going to be discontinuous at all. The only point where it could be potentially discontinuous would be at 0. Now, the only way it would be discontinuous would be non-removable per se, like if the one equation went up and then the other equation was like above or below and there was a jump in the graph. Well, when we type this on Desmos, this is great because we can see that the 2 points meet up perfectly. So this is a continuous function. Now, if we were trying to do this without a graphing calculator, this is what we'd have to do. Our potential discontinuity would be at 0. So what I'm going to do is I'm going to plug 0 into this equation and get a point. And then I'm going to plug 0 in for the other equation and see if those 2 points match up. If they exist at the same location, that means the open dot and the closed dot line up perfectly. So if I were going to take 0 and plug it into the first equation, 0 plus 1 is 1. Then if I take 0 and plug it into the second equation, 0 squared plus 1 is 1. So these match up, it's a continuous function. All right, the only other thing to look at here is the sine function. And so let's just graph that out right here. Now what does the sine look like? Sine of x. That just goes up, down, up, down. Sine doesn't have a denominator. We don't have to worry about anything like that. So this would also be a continuous function. All right. So really in this class, the only thing you need to worry about are the denominators. What would happen there? If we don't see any denominators, watch out. Piecewise function though, take a careful look at those points. All right, so I believe this is all we are covering today. Let me double check that by looking at the CYU. Yeah. All right, let's look at the CYU for today. See if we can make our life easier. So you guys are doing 1.4 CYU 1. Oh, okay. Yeah, totally forget about the next part we're going to talk about, left and right side limits. All right, so let's keep on looking at our notes here. Look at the next point. All right, what we're going to look at next is one-sided limits. So one-sided limits always exist as long as we look at the function. Now, if I have the limit as x approaches c plus, that means we're just looking at the limit going from the right side. And if I'm looking at the limit as x approaches c minus, that means I'm just looking at the limits going to the negative. Now we have this greatest integer function, which I'm just going to skip over this part here. I think it just gets more confusing than we need to go over. But let's look at some examples from the CYU. I think that would be better for us to look at. So what we're going to do here is look at this function. We have a graph here and our C is -2. I'm going to find the limit coming from the right side, coming from the left side, and then the overall function. And then I'm going to describe whether this function is removable or non-removable. And if it's, okay. So if we look at this point here, coming from the left side, coming from the right side, it's going down to -2. And then coming from the right side, it's going towards -2. Now our limit, we already know it has to be the same thing coming from the left, so this would be -2 as well. So if we look at this discontinuity point, this would be removable. And it says to type R if it's removable. Okay. Let's look at the next one here. All right, so coming from the right side, this is going up towards 3. Coming from the left side of the graph, this is going towards 3. What's the limit? Both of these? Both of them are going towards 3. Even though the point is at 4, the limit is going towards 3. Now, what kind of function is this? If all 3 of these match, this is a removable function. All right, now let's look at this one here. The limit as x approaches c from the right. If I'm coming from the right side, c is -1 here, I'm going down towards 0. Coming from the left side, we are going towards 2. The overall limit, though, we look, they are different numbers. The overall limit does not exist, D and E. So we would describe this function as non-removable discontinuity. Okay. So what I want you guys to do is go ahead and take a look at some of these problems here. You guys will plug these in, and we're going to look specifically going from the left and the right side. So you might want to use Desmos to help you out, and that probably make it a little bit easier. Once again, we got a piecewise function, so let's do this one together. So the piecewise function, if we didn't want to use a graphing calculator, we're going to go ahead and we're going to plug in 3 in for both of these, because that could be the potential discontinuous point. So the first point, if I plug 3 into the top, let's see, 3 squared is 9, and then -12 plus 6. All right, 9 minus 12 is -3, plus 6 is +3. All right, now we're going to plug it into the bottom here and see what we get. All right, 3 squared is 9, make that negative. All right, then plus 12 would be -3 minus 2. Okay, so that would be what, a 1? All right, so these do not match up, so we would say that this limit does not exist. Coming from the left side, it's 3. The right side is 1. Doesn't match up. This would be non-removable discontinuity that just does not exist. All right, guys, hopefully that helps out. We'll spend some time on this section. You guys have a great day, and I'll see you guys for the next part.